Hello and welcome you all to Knowledgeopedia. My name is Kuntal Ganguly and today we are going to discuss about electromagnetic flow meter and its history of development as of now, the core technology and its working principle. So today's era is about to automate the industrial process and future is on machine learning, artificial intelligence and its implementation through IoT platform. It's looks good, right? But to do carry out all those, I just mentioned you need to measure the process first, right? And today we are on the first phase of our discussion regarding measurement. And of course, this is my first video in YouTube channel, and request you to all like, subscribe, and share, and click on the bell button so that you could get notified whenever I release my next new video. So to measure anything in a bucket, it's always very easy, and as it is a static measurement, okay. But when some good amount of fluid passes through a pipe and operational process demands the exact quantity of it in a time interval manner is called a flow. The instrument gets used to measure the same is called as flow meter. As I hope it is now very clear to you all that what exactly a flow meter do, right? So let's have a look in a history of electromagnetic flow meters or EMF. So the history of development of electromagnetic technology and concept of its use for fluid measurement in domestic and industrial purposes started in the year of 1831 by Michael Faraday, who discovers the electromagnetic induction. Okay, in 1915, two American M.W. Smith and Joseph Sapien filed a patent for a device to measure the speed of boat by means of magnetohydrodynamics. Okay, so speed is very important here. So that is first invented in 1915. In 1930, same idea was adopted to close conduits by uh, Britton E.J. Williams. He's a British scientist. And in 1941, uh, Father von Vera Truman he researches the possibility to measure the flow based on Faraday's law of induction. In 1952, the first industrialization basically is a Toby meter. He's a Dutch scientist. He introduced first commercial electromagnetic flow meter. And finally, in 1962, the British scientist J.S. Radcliffe officially published the theory of electromagnetic flow measurement. So this is the complete development stage, one by one. I just have discussed with you, and you know that today there are many global manufacturer and renowned market player like Krone. They have started manufacturing in 1952. Yokogawa in 1955 around they introduced Japan first domestic electromagnetic flow meter. Emerson, it's a USA technology leader, entered in the field of around 1960. Anderson Hauser, it's a Swiss and German collaborated company. It's a family-owned business. They have started their manufacturing at Cerny, Switzerland. It's a very known village. I went there, and now it's a another German giant company, Siemens, who entered in the mid 1980 in this particular field. French company ABB, they started manufacturing at around 1960. Another company USA Asville, they have also started in 1990 or 94 around. Okay, so eventually the physical law of electromagnetic induction has been known for more than 100 years. As I already have discussed with you, it was only in 1950 when the first flow meter was made available using this technology. The electromagnetic field or EMFs become very popular in 1980 and 1990, when the performance was remarkably improved and different technology, another superior technology came in to improve particularly this measurement criteria, and purchase price also to buyer could significantly reduced. And today, the electromagnetic flow meters is the most commonly used flow meter in entire process control in many industries, as well as water and wastewater application worldwide. I think more than 1 million units are produced per year. So let's have a look at about the what Faraday did in 1833. It's a field test actually did by Michael Faraday. So this is the Waterloo Bridge. So Faraday tried to prove his theory by lowering two electrodes into the current of the river Thames on both ends of Waterloo Bridge. Okay, so these two are the electrodes. This is the Waterloo Bridge, and this has been placed across the Waterloo Bridge. Okay, across the Thames River. So he expected that the flow velocity would induce a voltage, since the moving conductor, that is the water of the river, is always moving through the magnetic field of the earth. So he was measuring a voltage, but unfortunately the induced signal was overpowered by the much greater signal noise. So signal noise, it's very common in such an arrangement, since electrochemical effects, static charges, and many other influences are present as well. So it's a flowing river, so there are many noise, and that particular days using specifically, it's basically there he's using the earth magnetism as magnetic field to generate magnetic field. Okay, so in particular that era of 1833, that time's signal filtering system, that means electronic suitability was not present that time. So it was, but yeah, the primary arrangement shows a possibility. It's generates a hope that definitely in future some technology we're going to come up to evaluate this signal which is generated uh, particularly in this field test. So there are two major components of flow measurement. One is flow rate, that is measurement against the time. Okay, that is flow rate. And the flow totalized volume, that is net volume flowed already have passed in a particular time. So that is a total volume of flow. Total, basically it's a net volume. So fluid may flow via closed pipe or an open channel. It's a closed pipe, and this is the open channel flow meter. Okay, so particularly for open channel, different types of channel shapes, okay, are used along with ultrasonic technology. So these are some different measurement aspect. Yeah, definitely in future I will discuss this particular technology also, because this are all have very huge amount of use in industry. Okay, so I will discuss in a separate video, or if you want me to release a particular video of particularly this purpose, then please let me know in the chat box. I will definitely come back to you. For closed pipe, today we are in the closed pipe technology, that is um, for closed pipe there are different ways of flow measurement. That means terms of volume or mass flow. Okay, and for volume, most common or most used method in the world is electromagnetic technology. Okay, so electromagnetic technology, this one, that is the most commonly used for volumetric measurement. It comes under volumetric measurement. Okay, this is the mass measurement, this is the volumetric measurement, and these are some mechanical arrangement like it's a direct or indirect measurement. Indirect measurement through like a vortex, swivel meter, turbine, rotary, gear meter, oval gear. This is some very old days meter like oval gear, oscillating piston, and some lobed impeller type of measurement. This all are, it's almost obsoleted. Okay, so in these days, normally this particular section are very important. in and today as we are discussing under volumetric measurement and in electromagnetic technology. Definitely for all this technology I will bring separate video in future. So please be with my channel. Definitely you will get more insight on this technology also. So, and today in my first video, we are going to discuss on the topic at a very basic aspect of understanding. Of course, in future, I'll be on my channel to get more videos and of advanced stage of measurement and other use technology. So let me know in comment section. So what is mass and what is volume? So mass basically is the physical value, okay? And it's simple, it's a symbol would be kg, ton, gram, etc. Okay, and it is not affected by fluid or process temperature or pressure because it's static value. Okay, it's a physical value which is not changeable. And for volume, it's basically a geometric value. Volume is the evaluation of how much three-dimensional space is occupied by an object. Okay, so like 1 liter of it's a symbol of liter, meter cube, cubic feet, etc. So mass flow rate, that is mass by time, that means kg per hour or kg per minute or ton per hour, ton per minute, whatever it is, it could be. And for volume flow rate, that is volume for time, volume per time, that means it could be meter cube per hour or liter per minute. As you know, since majority of production process system operates continuously, the continuous measurement is required because the measurement value must be representative of the instantaneous condition or indicate the instantaneous values. Therefore time related value is very necessary. It is known as flow rate. Okay, so based on that flow rate, different process parameters are adjusted, different valves are gets opened and closed, and different process are maintained. Okay, so let's have a look at the basic working principle of Faraday's law of induction. So Faraday's law of electromagnetic induction is the basic principle of any EMF instead of a wired move within a magnetic field formed by a permanent magnet. It's a permanent magnet. Okay, a conductive liquid passes through an alternating magnetic field generated by the coils. These are the coils. Just above the and bottom there is two coil. Okay, and which is continuously generating the magnetic field. To measure flow based on the Faraday's law of induction, alternative magnetic field is produced with coil of proper copper wire. Okay, a controlled current ensures that the magnetic field strength remains constant during the measurement. Okay, so magnetic field strength, that is the UI, it is always common and it is static. Okay, the length of the conductor, that is the distance between the two measuring electrode in the internal diameter of the measuring tube, is also a constant value. That means the diameter. This one is the measuring electrode and another measuring electrode is here. So if this is the pipe diameter at and both end there are two electrodes are placed, and the distance between the two electrodes, that means the diameter of the measuring tube or pipe, that is a constant value. Okay, the diameter cannot be changed, right? So the only variable of the above equation is the flow velocity, right? The flow velocity of the passing fluid, the generated voltage is exactly proportional and linear to the velocity of the fluid. And EMF doesn't measure volume directly, but measure the velocity. Okay, so velocity, how does it measure? These are the two electrodes placed at the both side, and there is a constant magnetic field created by these two coils. Okay, and fluid media, suppose it is flowing from left to right. Okay, it's whenever it passes through, it's a conductive medium, it generates an induced voltage. Okay, these are the induced voltage, and this induced voltage is directly proportional to the velocity of the fluid. That means what? That ui, as I already have told, that is the magnetic field that is constant. This L, what is this? That is the length of the conductor. Okay, and magnetic field strength, that is B, that is also a constant. So only the variable parameter comes out, that is V, that is the velocity of the flowing medium. Okay, so to get the volume flow, the measured velocity is multiplied with the known and fixed cross section of the measuring tube. Okay, because because of this approach, it is crucial for a reliable measurement to maintain a full pipe at all time. This is very important. I will come back to this point later on. Okay, so if this is the cross-sectional area, so what would be the uh, unit of velocity? It should be something around meter per second, right? And what would be the cross-sectional area? That is pi d square by 4, and the unit will come up as meter square. So if you going to multiply that meter square with meter per second, that means it comes up as meter cube per second, that is volume. Okay, so volume, that does what would be the uh, unit of that would be meter cube per second. And if you are going to multiply it by 3600, that means per second value to per hour value, it will represent the meter cube per hour value. So per hour, that means after an hour, particular if it is comes out at 200 meter cube per hour, that means after an hour a totalized volume of 200 meter cube, that means 2000 kiloliter of that much of water or liquid will pass through. Okay, that would be the totalized value. Simple. If the flow rate is 100 meter cube per hour comes out, that means after an hour totalized value would be 100. So the EMF is capable to measure the flow rate in both directions. Based on the polarity of the induced voltage, one can detect the flow direction. So flow direction can be achieved or determined by the polarity of that coil. Okay, so if this coil is positive, this one is negative, that means suppose a direction comes out, that is as per Faraday's law, that it be from left to right. Okay, in case I just reverse the polarity, that means the bottom one would be the positive and upper one would be the negative. That means what? The flow direction, positive flow direction would be from right to left. Fine. So whenever the measurement will happen, if it is a both direction flow available, that also can be identified. Okay, so let's have a look with the presently available mechanical design of the electromagnetic flow meter sensor part. Okay, so this is the internal structure of the electromagnetic flow meter sensor part, and the sensor that is comprises of all parts and functions of the device mounted in the pipe. It's a hollow body basically. Okay, so process connection, this is the process connection that provide connection to customer process piping. Choose from any option, that could be NC, that could be PN40, PN16, PN other, that screwed connection, that could be triclamp version for food and pharma. It's widely available of process connection, that is depends upon the manufacturer one by one. These are the liner material. So why liner is used? Liner is used basically for to isolate the induced voltage from tube, that must be resistant uh, against the medium. and you need to choose carefully available options in market, as I think that is mostly used, that is ebonite, linatex, ptfe, PFA, polyurethane, hard rubber, natural rubber, PU, etc., etc. So many options are there. Okay, it depends upon the flowing medium. Basically, if you are using a fluid, it's a if it is a clean liquid. Okay, so you can use hard rubber or ebonite or anything. Okay, in fact, PTFE is also working well, no problem. In case of suspended impurities are very high, okay, that's like 5%, 10%, or somehow 30, 50, 60% even, or 70% mostly available for a slurry application. That times you must go for linatex, okay, or soft rubber or natural rubbers. Natural soft rubber can be a very useful solution for that particular option. Okay, sometimes for water and wastewater plants, their different chemicals are being mixed. In that particular area, ebonite would be the best solution because of the chemical compatibility. Anyway, so now I'm coming in to the electrode section. These are the two electrodes, as I already have lastly showed you that how the electrodes are placed in a flow meter body. Okay, that is that is for to detect in instrument measurement signal that must be resistant also against medium. Several material are available as the standard option, like stainless steel, alloy C22, monel, tantalum, platinum, rhodium, etc. So different options are there. For coil system, these are two coil system you can see. Coil system generates magnetic field to it to design to get the most homogeneous fluid. That means that should be well mixed. Okay. Now for transmitter option, yeah, that is for transmitter, basically amplifies and filters the signal. Okay, this is a transmitter. That transmitter basically amplify and filter the signal received from the sensor area and computes it to relevant data like totalizer, flow rate. It generates the interface signal also for hard profibus, etc. Suppose in the transmit from the transmitter you need to have the retransmission signal to your PLC or DCS or any other uh, viewing medium or other host system. So from transmitter, anyone could achieve a separate output according to the flow or according to the uh, measured data for with a heart, profibus, foundation field bus, mod bus, 4 to 20 milliampere analog signal, whatever. That is the HMI and display. Okay, HMI, that means human machine interface. That means you can adjust the different parameters through the push buttons or any other medium like heart communicator and all. That can be mounted integrally. That means it could be mounted just above the flow meter, and for remote, depending upon the installation situation. Remote, that means the transmitter could be separated from the sensor through cable. Okay, so one of the advantage of electromagnetic flow meter is the design without obstruction. You can see there is no obstruction. It's the finished product. You can see, yeah, there is no obstruction to the flowing process fluid. That means the meter provides measurement without any additional pressure loss. Okay, and the full bore without any moving parts means that the meter can also be very easily cleaned. The cleaning is very easy. This particularly or this partially in fact explains the attractiveness of the meter to the food industry. Okay, because the cleaning area, they usually periodically runs the CIP or cleaning in process. Okay, so cleaning is very much important aspect of the flow food industry or pharma industry. So there is uh, they are very attractive. This is a very attractive option to the food industry. So more importantly, however, no moving parts or obstructive surface to wear usually translates directly to a longer life in a service. Okay, and an overall good investment. So whatever you are investing, you will get a good return because it's a very long life flow meter. In addition, the flow meter is inherently bidirectional, as I already have explained how it could be. This can be a tremendous cost saver for many applications. Okay, and especially the accuracy. At the recent days, the accuracy of magnetometer is very excellent. Typically 0.5% is for normal for reading for standard models, and down to 0.2% for some high accuracy models available with some global manufacturer. Okay, in addition, the meter's accuracy is not affected by changes of process fluid parameters such as temperature, density, and viscosity, as I already have discussed how it could be. Okay, for temperature, density, and viscosity, these are not affected. Okay, as long as the fluid is relatively homogeneous, that is well mixed, as it passes by the meter, the measurement will be stable and accurate. The magmeter is also fully capable of handling clean fluids as well as slurries or fluids with large percentage of solids. That means slurry. I already have explained. A general rule of thumb is, um, if the fluid is conductive, number one criteria that should be conductive, and which can be pumped. That means through pump you can uh, have the fluid transferred. It can be measured by a magmeter. Okay, that means number one, that should be conductive and which can be pumped. This can be measured by magmeter. The magmeter also has an excellent turn down ratio. That means the ability to accurately measure flow from zero point 0.1 1 meter per second to 10 meter per second, means a magmeter can be appropriately sized for the vast majority of application found in the process markets. Magmeters which can be available on the market from 2 millimeter of nominal diameter up to 4 meter. The wide variety is available from. It's a huge turndown, you can say. The measuring principle is essentially the same for all sizes, and only construction details may differ. Okay, it depends upon the manufacturer by manufacturer. That's the construction details that definitely it could be difference between one manufacturer to other manufacturer. Okay, but the main core technology are always same. The magmeter has a large advantage as it is far more forgiving to upstream flow profile disturbances that most other competing flow technologies are having. Okay, that means flow laminar profile of flow is not that much of important in magnetic flow meter. This is primarily due to the fact that the induced voltage on the magmeter measuring electrodes picks up the velocity information from the fluid particles throughout the full cross sectional of the meter. Throughout the full cross section of the meter, it picks up the velocity information. That means it creates a flow profile, a very wide variety of flow profile. It already having the capability to create. So unlike differential pressure flow device, through differential pressure device also you can measure flow. It's a separate technology. Okay, the output of a magmeter is very much linear. Its linear output represents a response in a linear fashion to change in flow. This means no additional characterization of signal is required, which can be especially beneficial in control application. If you are controlling anything, or you are controlling any process from the output of the flow meter of electromagnetic flow meter output, you are controlling a particular process, like you are going to shut off a valve or partially close a valve or open a valve. That means you need to have very linear kind of input into the controlling medium. That means the control valve or PLC. And from magnetic flow meter you will get that linear signal. It is not a non-linear signal, and you need to recreate a particular signal shape from that non-linear input. It's already giving you a linear signal, which is very much beneficial for a control system designer or a PLC uh, program developer, it's a very easy job for them. Okay, and lastly, Mac meter are available in a wide variety of material for weighted parts. That means the liner and electrode, making them easily applicable to across a vast array of processes and services. So, as I already have told you that the conductivity of liquid is the uh, primary importance for a magnetic flow meter to design with. So let's have a look at the ranges of conductivity of the liquids. The most fluid with the with little conductivity can be sorted in three groups. Okay, there's three groups. One is from zero point zero 0.05 microsiemens per centimeter to 1 microsiemens per centimeter, and the second group, that is around 10 microsiemens of centimeter, and the water, it's EMF in water, that is 100 microsiemens per centimeter to somewhere around 1000 microsiemens. Okay, sorry, millisiemens. So normally electromagnetic flow meters are used in these two criteria only. Yeah, we have some other option for 1 microsiemens also, but this is very rare. Okay, so suppose demineralized water or ultra pure water. Ultra pure water, that means it's having a very low conductivity. Okay, it comes in this range. Okay, or suppose pure oil or mineral or and organic and hydrocarbons, gasoline, solvents, motor oils, etc. And the third group is liquefied gases. The fluids cannot be measured with the EMF, but they represent only a very small part of all known and measured liquids. By far, the most liquids are well above the minimum conductivity limits or minimum conductivity requires for an EMF measurement. Uh, as a physical limitation, the induction requires a minimum conductivity to be functional. For general purpose EMF, the limit is somewhere around 5 microsiemens per centimeters. Most manufacturers are available with this with the flow meter of electromagnetic technology from 5 microsiemens per centimeter. Okay, but yes, there are some renowned manufacturer who does offer from 1 microsiemens per centimeter even. Okay, so I will come back in this particular in advanced stages. I will explain how this could be achieved. Okay, and what are the different technology behind it, and additional add-on. Okay, an add-on of the base core technology to achieve this much of functionality. So all available liner material are isolating plastic with a limited operating temperature. This is the limiting factor of the applicability of EMFs. Whilst magmeter is very tolerant regarding buildup on the measuring tube, there are limitations. A layer on the electrodes will finally lead to a reduced flow signal and the device will stop functioning. That means what? That very small part of of the explode area, that is the electrode, that is two measuring electrode. If any layer of conductive or non-conductive coating is there, so it will finally lead to a reduced flow signal or more accelerated flow signal. If it is a conductive coating, it will create a more basically it will create a short circuit, so it will um, accelerate the flow signal, which will damage the flow meter or which will give the wrong signal level. Okay, so measurement and calibration uncertainty. So what is because this is the part, mostly the design aspect or mostly the selection area of purchase person basically, or technical purchase person, who used to have a look before purchasing of any flow meter, you can say, not only electromagnetic, any flow meter. Anyway, what exactly does it call about the calibration uncertainty? So accuracy and repeatability, this is the there is a difference. What is accuracy? Here you can see the accuracy. It's very accurate, okay? So what is the difference of this and this? This is also very accurate, you can see. Sorry, this accuracy is very high, and also repeatability is very high. So both accuracy has been repeated once, again and again. This particular example in C diagram, you can see this accuracy is not there, but repeatability is there definitely, because whatever the accuracy it is getting achieved, it's again and again hit. Okay, and this one is neither accurate nor repeated, so it's something not useful. Okay, so accuracy is how close a stage can position to a actual value or true value. Repeatability is the measure of the stage ability to sequentially position to the same target value again and again, hitting the same target value. It is important to understand that accuracy and repeatability are two different properties of a positioning system. In a number of applications, the repeatability of a motion system is more important than the accuracy. Okay, like systematic errors can be taken into account and compensated, but the repeatability is the ultimate limit that is reached after all compensation, right? So how it could be achieved? Like suppose you are using a rotary filling machine in a food and pharma industry where 200 mLs of Coke or Pepsi are getting filled in each and every bottle. Okay, it's a rounding machine. It's a round machine, and one by one flow meters are installed one by one, and behind that a belt is rotating, and from there one by one bottles are placed, empty bottles, and whenever each bottle are coming in front of the nozzle that is connected with a flow meter. Okay, flow meter is giving or passing exact amount of 200 ml of Coca-Cola or Pepsi into the particular bottle, and it is passing through and coming, waiting for the next bottle to come in. Again, same amount of liquid are getting filled and is passing through. Suppose one flow meter, that means what? It means that all the flow meters are installed in this particular machine are having both accuracy and repeatability. It's hitting again and again. This is the example of this A parameter. Okay, suppose out of whatever the n number of meter installed in a particular filling machine, 1 or 2 meter are not exactly accurate. That means what? Out of 200 ml, those flow meters are passing 170 ml of Coke into a bottle. So what that means that you need to compensate that 30 ml, whatever the shortfall is there, the 30 ml liquid again and again whenever the any empty bottle coming through that particular flow meter of effective flow meter. Okay, that means what? That flow meter should be should have a good repeatability. That means 170 ml at least it has to reach every time. It should not be like that in one occasion it is giving 200 ml correct amount, second time it is overflowing and giving it to 230 ml, third time it is giving 170 ml. That means this much or this type of behavior is not accepted there. If it is giving continuously 170 ml, 30 ml, you can compensate through the system. Okay, from the filling system you can compensate that 30 ml. Or if it is giving 230 ml every time, that means 30 ml excess value can be reduced systematically. Okay, so that means what? The accuracy, and between accuracy and repeatability is the most important factor, and repeatability must be achieved. Accuracy is the secondary one, but definitely it's also a very important thing, but repeatability is the most important. So regarding let's have a look of the some recent technology of pulse DC magnetic flow meter. So how that pulse DC magnetic flow meter works, I already have given few idea that about um, how the structural design uh, suppose in a the coil polarity of positive and negative direction can be altered. Okay, so whenever you are altering a pulse or a magnetic field, that means you need to create a different end of signal, like u plus, that is the most highest signal of noise, and the u minus signal, that is whenever the DC pulse field has been changed. Okay, so we need to evaluate that particular u flow, that means flow value, by evaluating the maximum and the minimum signal dividing by 2. Okay, so that means the graph shows basically the concept of the signal generation and the calculation of the flow velocity. Because of the alternating polarity of the magnetic field, the induced voltage is changing the polarity as well. Okay, it's changing the polarity once again. Huh? So all noise signals are not induced voltage and keep the polarity all the time. Okay, polarity. So all polarity will not get changed, because whatever the noise signal, that has to be eliminated at the end of the day, right? So by simple subtraction of the induced voltage signal can be calculated and the noise could be eliminated. Okay. In a very noisy application, it becomes more and more difficult to separate signal from noise. These are several technical approaches to improve the performance of an EMF in critical application. High accuracy application, there are very much important to measure the flow rate from minimum possible area. Okay, that means minimum velocity that could be measured. Okay, the graph shows the concept of the signal generation and the calculation of the flow velocity. Because of the alternating polarity of the magnetic field, the induced voltage is changing polarity as well. All noise signals are not induced voltage and keep the polarity all the time. By simple subtraction of the induced voltage, the voltage signal can be calculated and the noise could be eliminated. In a very noisy application, it becomes more difficult. Okay, but there are several technical approaches to improve the performance in future. Okay, so these are the simple thing, basically the noise background, that is this one, this much a portion that could be eliminated. That means that these are the cutoff signal, right? This cutoff signal must be eliminated. Fine. So I hope you have got the basic idea about the electromagnetic flow meter development history and its background technologies, major manufacturers, recent developments, and its parameters in details. Okay, if you want to have more insight on this technology, installation criteria, and any specific in details, please let me know in the comment box. And of course, at the last, your if you like the video, don't forget it to like, subscribe. This encourages a lot, brings such an interested video in future. Thanks for watching.